So I want to evaluate the integral from 0 to infinity of sine squared of x over 1 plus x squared. So first I can use a relation that says that sine squared of x is equal to a half of 1 minus cosine of 2x. And so I can rewrite it as 1 over 2 times the integral from 0 to infinity of 1 minus cosine of 2x over 1 plus x squared. Okay, and now this is an even integral here. So I can rewrite it as this integral from 0 to infinity, and can rewrite it as half of the integral from minus infinity to positive infinity. Okay, so at the end we have a fourth of times the integral from minus to positive infinity of 1 minus cosine of 2x over 1 plus x squared, okay, dx. And now, as said in the last video, whenever you have something like cosine or sine in the denominator, so above the bar fractions, it's really useful in complex analysis to write it as the real or imaginary part of e to the ix, okay? So here we have cosine of 2x, so we can rewrite the entire thing as the real part of 1 minus e to the 2ix, okay? There's a 2 here because we have a 2x inside here, okay? So at the end we have 1 over 4 times the real part of the integral from minus to positive infinity of 1 minus e to the 2ix over 1 plus x squared, okay? So now, first we will do a quick manipulation, e to the 2ix, okay, so the thing here can be written as e to the 2ir e to the I theta, when x is set equal to r e to the I theta. Okay, why we will do that? Well, you will see in a minute. But let's suppose x is equal to r times e to the I theta. And so now you replace this x with this value here. Now you can use Euler's formula. So e to the I theta is equal to cosine theta plus I sine theta. Okay, and so that's what we do here. So we have e to the 2ri times cosine theta plus I sine theta. Now we can take the I inside and we get e to the 2r times I cosine theta minus sine theta. Okay, we have an I here and an I here, so we have an I squared, so we have minus sine of theta. Okay, so now if we let the radius go toward infinity, if you want to get an exponential decay e to the minus infinity that will tend toward 0, we need sine of theta to be positive, okay, so greater than 0, okay, because if sine of theta would be negative, here we would have negative, negative, so positive, and so we would have e to the infinity at the end, okay, and that would diverge, and that's not what you want. So to do that, so we need a sine of theta positive, and it is only positive if we have a counter integral along the upper half plane, okay. If we add it in the along the lower half plane, so this is the real axis, here too this is the real axis, and that here and that here are the imaginary axis. If we would have something in the lower half plane, sine of theta would be negative, and so it would diverge. So to evaluate this integral, we need a contour along the upper half plane, so it goes from minus infinity to positive infinity, and then along a circular path back to minus infinity. But this circular path is in the upper half plane, not the lower half plane. Okay, in the lower half plane, this would not converge if we do this manipulation, and so it would not work. Okay, so why do we do that? You will see in a minute. So first, as usual, we calculate the poles. So 1 plus x squared is equal to 0. So x is equal to plus or minus I. And so we have a pole of order n is equal to 1, okay, because it's a third order pole, okay. Everything here is to the first power. There is nothing squared to the third power whatsoever. It's only to the first power, okay. And so we can use the formula for residues of pole of order 1. So that is that everything above the fraction bar stays the same, but everything below it, we just take the derivative of it, the first derivative. So we take the derivative of 1 plus x squared, okay? So this, yeah, the 1 plus x squared. Yeah. So the derivative of 1 plus x squared is simply 2x, okay? And everything above it stays the same, so 1 minus e to the 2x still stays the same. And now if we have the path set in the upper half plane, we have two poles, plus and minus I, but only positive I is inside it in this case. And so if we evaluate x is equal to I in this formula here, we get the following. We get 1 minus e to the 2i times I over 2i, and so that is equal to 1 minus e to the minus 2 over 2i. Okay, and so that will be our only residue in our domain, because as said, negative I is not in our domain. Now we can split our contour integral into two parts. The part along the real axis from minus infinity to positive infinity, and the path along the circular half circle. Yes, so the path along the upper half circle that goes from infinity to negative infinity. So there I said for the second path, so the first path, the first part, so the number 1, so from negative infinity to positive infinity, is our integral, so our original integral. It goes from minus infinity to positive infinity. And now the goal is that we want to prove that the second part, so the part along this half circle, vanishes as our radius r tends toward infinity. That's why we made this discussion here before, why we let x is equal to r e to the I theta, because we need the integral to be convergent and to tend towards 0 when the radius gets toward infinity. And for that, we need to get an exponential decay, so something like e to the minus infinity, as written here. And so we made this calculation before and saw that for that to occur, sine of theta needs to be positive and not negative. If it is negative, so in the lower half plane that would be the case, then it would not converge. We would get e to the infinity, because we would get minus sine of theta, but sine of theta would in that case, as it be negative, so we would have minus minus, so positive, and here we would have our r, which tends towards infinity, always positive infinity, because a radius is a geometrical distance, and the geometrical distance cannot be negative, and so we would get e to the r times something positive, so e to the infinity, and that would diverge. That's why we made all this discussion before. Okay, we saw, okay, in which conditions can I get an exponential decay, so I need to the minus infinity, and only in those cases should I proceed, because otherwise we won't be able to move on. Okay, because the whole thing would not converge, and thus we would be stuck in this part. Okay, so here, sine of theta is positive. So first we will let our x be equal to r times e to the pi I t. Our t will be between 0 and 1, because we're going like this. Okay, if I said we would do something like that, so in the lower half plane, t will be between 0 and negative 1, but this is not the case here. Because I said this would not work if we did it in the lower half plane. Okay. Yes, our dx will be equal to pi I times r times e to the pi I t dt. So this is why if we simply take the derivative, we get that dx. So now we can plug in everything. So we get the integral from 0 to 1 of 1 minus e to the 2ir e to the pi I t. Notice that, we will talk about that in a second. Here we have our dx, which is now pi I r times e to the pi I t dt. Okay, that is that part here above. And here in the denominator, we just replace x with this r times e to the pi I t. So we get 1 plus r squared e to the 2 pi I t. Okay. Yes. And so now we are going to do two things. So first, As said, the whole point is to prove that the second part vanishes as r gets larger and larger. Okay, if r tends toward infinity, so the radius gets larger and larger than tends toward infinity, we want to make sure that the second part vanishes, so that you're only left with the first part, 1, along the real axis, which will be our original integral. And then you can use the residue theorem to evaluate this integral and we're done. Okay, but for that, I said the second part, the second integral along the upper half circle needs to vanish. That's why we're doing that. So the part with the exponential, so e to the 2I r e to the pi t, we're going to get an exponential decay for that. And for the one, we will talk about that in a few minutes. Okay, we will also make it disappear. So for the exponential, so we can write this e to the pi I t inside the exponential using Euler's formula. We can rewrite it as cosine of pi t plus I sine of pi t. Okay, and so we can rewrite the e to the 2I r e to the pi t as e to the 2I r times cosine of pi t plus I sine of pi t. Okay, that's what we did here. Now we can take this I inside, and as we did before at the beginning, that's why we did everything at the beginning. We're doing the same thing now because we know that it's going to work and that it's going to give us an exponential decay. That's why we're doing it, and that's why we did it before, to be sure about which direction we should choose and how we should proceed. That's why we did the entire thing at the beginning. Anyway, so here if we take the I inside, we have now I times cosine of pi t minus sine of pi t, because for the same reason as before, at the beginning we have this I here and this I here, so we get I squared, so it's -1. So you have negative sine of pi t. Now I said in the upper half plane, sine of pi t is positive, and e to the I cosine pi t, so this part here, is bounded, okay, because we have an I here, so we have something like e to the I theta, and that is bounded by definition, okay. E to the I theta, by definition, the norm of it, the length of it is equal to 1, because this is a circle of radius 1, okay. So by definition, e to the I theta is bounded, so e to the I cosine pi t is also bounded, and so it is not going to diverge, because it cannot, okay. This is a circle, after all, that turns and turns and turns and so on, okay. Yeah, or maybe in the opposite direction, I don't know. Anyway, so this is bounded, so we don't care about it. We only care about the sine of pi t, because it needs to be positive for the entire thing to be negative in the exponent, okay? That we get e to the minus infinity, so we know that r will tend toward infinity, so the radius will tend toward infinity. And now, to get this exponential decay, I said, we already have a negative in front of the sign, so sine of pi t should be positive, because if it is negative, you would get negative, negative, so positive. And I said we will get e to the infinity, because the radius, I said, it's always positive, because this is a distance, and so we would get e to the r positive, and so we will get e to the infinity, and that will diverge, and that's not what we want. So here I said sine of pi t needs to be positive, and that's why we chose this entire contour and not another one. And so I said we get that at the end you get e to the minus infinity, which will tend towards 0. Okay, that's why we did the whole thing here before. Okay, sorry, here in this region. So I said we choose it correctly, and so the second part will now vanish, but first we also need to prove that the 1 here also vanishes. And for that, remember everything that in this region here, so we substituted dx with pi I r to the I pi I t dt, and also in the denominator we substitute x squared with r squared e to the 2 pi I t, okay, because x is equal to r e to the pi I t. And so basically what we only need to consider is that roughly, so already this exponentially it will vanish, it will go towards 0, okay, it will be an exponential decay, as said here. So now if we consider only the 1, it will also go to 0. It will also go to 0. Why? Because we have this r here from the dx, okay, that pops up here, and in the denominator we have x squared, okay, and the third we replace it with this r e to the pi I t, so squared will give us this r squared e to the 2 pi I t, okay. So we get an r squared here and an r here, okay? And so roughly this integral, if r gets larger and larger and tends toward infinity, is roughly equal to r over r squared, which is equal to 1 over r, which will tend to 0, okay, if r gets larger and larger, okay. And so the part with the 1 will also tend towards 0, okay, maybe less quickly than the exponential part, but still it will also tend towards 0, okay. So well, now we can say for sure that the second integral, so along this upper half circle, will tend towards 0 as the radius gets toward infinity, okay. So now we can apply the residue theorem. So we have that our counter integral, so which is made of the part 1 and 2, so the part along the real axis and the part along the upper half circle. So 1 here, I hope you can read it, and 2 here, okay. This part here is 1. So this counter integral is now equal to our original integral, so the part 1, okay, or the part 1 is our original integral, and the part 2, as said, will vanish, will go to 0 as our radius tends toward infinity. And so that is equal to 2 pi I times the sum of the residues. And so remember, the residues were somewhere here, I think. Here is our only residue inside the upper half plane, only x is equal to I is inside our domain, because x is equal to negative I is not inside it, okay? Only I is here inside somewhere, because negative I would be somewhere here, and that is outside our domain, okay? As I said, this negative I would be inside our domain if we had chosen the lower half plane, the lower half circle to do our computation, but in this case, the integral along the second part, so along this circular axis would not converge, and you would not be able to proceed, and so that would not help us further, okay? That's why we choose the upper half plane, okay? I really want to emphasize that because this is very, very important. Okay, so now, so our only residue, I said, is this 1 minus e to the minus 2 over 2i, and so now we multiply it with 2 pi I, and we get pi times 1 minus e to the minus 2, okay, because the 2i here, so the 2 and the i here, will cancel with the 2i here in the denominator, and so we only have pi times 1 minus e to the minus 2, and so this is the value of our integral, of this integral here, okay, so not our original integral, because remember that our original integral is equal to a fourth time the real part of the integral we found here, okay? Remember our sine squared of x plus over 1 over x squared, we made some manipulation to first convert that into a cosine of 2x and some other stuff, and now we took we considered this integral, and so that this is the real part of 1 minus e to the 2ix, okay, you cannot read it, but still it's the same thing. It's the real part of 1 minus e to the 2ix, okay, I hope you can read it. Yes, and so at the end we know that our original integral is simply equal to a fourth, so 1 over 4 times the real part of that final result, okay? So if we take the real part of this pi times 1 minus e to the minus 2, well, this is the same thing because there is no imaginary number at all in it. So the real part of pi times 1 minus e to the minus 2 is pi times 1 minus e to the minus 2, and now we take we divide by 4, okay, and so we get this value here, okay, 1 over 4 times pi times 1 minus e to the minus 2, which is our final results. And surprisingly, in Wolfram alpha, the numerical value of this whole thing here is is equal to pi times sinus hyperbolicus of 1 over 2 times e. Okay, strangely, I don't know, but okay, so this representation here would also be valid because this is the same numerical value. Okay, I don't know how you can go from this part here to this part here, but it gives the same numerical value, and so logically it should be equal. So how you go from one to the other, I don't know, but it works. Just that you know it. Yes, so that's it. I hope it was clear. So to remember, so what we did first, we converted the sine squared of x into a 1/2 times 1 minus cosine of 2x, and then this 1 minus cosine of 2x, we wrote it as the real part of 1 minus e to the 2ix. Okay, we wrote it as the real part of that. And now we evaluated everything with 1 minus e to the 2ix, because as said in complex analysis, I don't know if I said it in this video, but in others I did. If you have something with cosine and sine, it's a lot easier to convert that into the real and imaginary part of e to the ix or e to the 2ix, because we have cosine of 2x. Because it's a lot easier to do with e to the ix than with sine of x or cosine of x in complex analysis. So if you can do that, do it, because that is in almost all cases the right path to choose. Okay. So then we converted that, and we saw for which values of sine the whole thing can convert, so that we get an exponential decay, and we noticed that we need to evaluate it in the upper half plane. Okay, and then we found our poles, and we calculated our residues that are inside our domain, and then we proved that the part along the circular axis vanishes as r gets larger and larger, and that's this result was due to our calculation before to see for which value the integral will vanish along the circular axis. So this was expected in this part here, because we saw it here in this part. Here in this part, yeah, it's really ugly. And yeah, so we proved that it vanishes here and here, so for the 1 and for the exponential. So the exponential, we have an exponential decay, and for the 1 we have roughly r over r squared. Okay, this r is from the dx here, and the r squared in the denominator, because there is an x squared in the denominator, so we know that x is equal to r times e to the pi I t here for the circular axis, or for the path 2. And so we get roughly r over r squared, so 1 over r, which will tend to 0. This is 0 here for r toward infinity. Okay, and remember, the radius is always positive, because a radius is a geometrical distance, and the geometrical distance is always positive. So we proved that the contour integral along the part number 2, so along the circular axis, circular half circle in the upper half plane, goes to 0, and then we can use the residue theorem. The second part vanishes, as I said, it is 0, and the first part along the real axis is our original integral, and that is equal to 2 pi I times the sum of the residues. Okay, so 2 pi I times the sum of the residues, and as said, this is our only residue inside our domain. So if you multiply it with 2 pi I, we get pi times 1 minus e to the minus 2, which is our integral with 1 minus e to the 2ix, and we saw that our original integral is 1 over 4 times the real part of this integral with 1 minus e to the 2ix. Okay, so if we take the real part and divide by 4, we get our original integral here, and we're done. Okay, and surprisingly, the numerical value of this result is the same as pi times sinus hyperbolicus of 1 over 2 times e to the first power. Okay, this is 1 here, don't write it, but still. So both results should be equal, but I don't know how you go from the first to the second, or from the second to the first, but still it works. Yeah, and yes, I hope it was clear. Also, don't forget that here we went from the integral from 0 to infinity to the integral to half of the integral from minus infinity to positive infinity, because this integral here was even. Okay, even if you cannot read it now, because there's a lot of writing, still this integral here was even, so we were able to split it. Okay, remember, if you have an integral like 0 to infinity of something even, this is half of the integral from minus to positive infinity of this same function. If the function is even, again. If it's not even, you cannot do anything. But here it's even, so we use it, okay? Yeah, otherwise I don't know how you should proceed. Maybe there's a way. Maybe there is a way, but yeah, I haven't tried to find it. Yeah. So I hope it was clear, and yeah, thanks for watching. Yes.